just to make sure that we have this take-home term. Week long. I posted on March 4th. And the due date is March 11th. And so this week, I posted regular homework number 6 due March 4th. And then after that, you will get this the midterm, take-home midterm instead of a homework. So that's the idea. And I told you that you are not supposed to use any help from human beings, internet. But it is open book in a sense that book can be lecture, videos, slides, notes, and textbook. So that's the idea. So, are there any questions about this? Yes.
Can we use the homeworks?
I'm sorry?
Can we reference a homework if we need to?
Oh, yeah. I should have said homework solutions. That's what you want, right?
Well, yeah.
All right. So let's get. Yes.
Can we use Mathematica?
Oh, Mathematica.
It's like a calculator.
It's a bit of an issue that some of you have access, some of you don't. Who have access to Mathematica? And who don't? And if you do want to have access to Mathematica, what are the ways? Do you have to buy one?
I think you can
No,
download
you can,
Yeah,
you can access the website.
So everybody has access?
Yeah, free.
Oh,
Oh, okay. So then,
It's just.
so you just need to download it
Yeah,
and
yeah.
get used to it. Well, then I would say fine, yeah, because I just was worried that if that might create some unfair situation, but apparently it doesn't. So everybody's okay with that?
Yeah.
Okay, then you can use Mathematica.
But, okay. Mathematica has some packages that can, maybe it offers some functions that can calculate your problems directly. Is that okay?
I kind of doubt it, but so let's say no packages are allowed, just the
Okay.
plain Mathematica you download and install. Would that make it fine? Okay. Okay. So then I should put that also in the policy. You should sign. All right. So we spent a lot of time talking about bosons. So what we discussed is that we started out with the usual commutation relation among creation relation operators. We introduced a lot of them. And eventually, that became the field. And we had a Lagrangian form. And we also looked at this point that this is totally equivalent multi-particle quantum mechanics of identical bosons, because we could write down any generic state using creation operators. Acting on a vacuum, and you take linear superposition, with this function cardinal psi, and this turns out to have the meaning of Schrödinger wave function. in addition, we looked at the problem when the chemical potential is positive, and that's a problem you couldn't solve using the quantum mechanics, but we could using QFT, and we have this weird ground state, which is the coherent state, and therefore linear superposition among the states with different number of particles in it. And you're also now looking in the non-zero momentum mode, where you have to do this Bogoliubov transformation to find the ground state of the system. And that way you can even work out the extension spectrum of the system, and that becomes this Bogoliubov spectrum, which I showed really beautifully agrees with experimental data. So that's what we have done so far. And as many of you asked me already, so the natural question next is, what are the fermions? In the case of fermion, as you know from quantum mechanics class, you cannot occupy a quantum state more than once. And this is what people call the Pauli's exclusion principle. And this is the way you could understand, for example, the behavior of the atoms. We have nucleus, we have one s orbital, and you put one electron with spin up, another electron with spin down, then you cannot put any more electrons into one s orbital, because this is one quantum state that's now occupied, here's another quantum state that is now occupied, and this becomes the helium atom. And the same thing if you go to 2s, again you can occupy it one each for each spin state and so on and so forth. And that's the way we understand the stability of atoms, right? Otherwise, all the electrons would get down to the oneness state, and that's not what we see to understand the periodic table in chemistry. And the next thing you learn in quantum mechanics is the Pauli's exclusion principle is actually a consequence of the fact that wave function is anti-symmetric if you interchange here I and j. So when you interchange two particles, the wave function is anti-symmetric. And consequence of this is that whenever these two, the positions are the same, being anti-symmetric, when x and x are the same, wave function just vanishes. And that's the way you can see that you cannot occupy the same quantum state, for example, the same position eigenstate, by more than one particles, and that's the Pauli's exclusion principle. So what we need to figure out is how we can implement this in quantum field theory. And I go straight to the answer. It turns out that instead of this commutation relation for bosons, what you need to do is to use anti-commutation relation. So the idea is that when you have an annihilation operator, let's say B, and creation operator B dagger, what you have is anti-commutation. So instead of minus sign, which you had for A in A dagger, that was 1. Instead, you put plus sign. And that's the meaning of anti-commutation relation. And this is 1. And similarly, when you have two annihilation operators, and using this definition of the curly braces, this is BB plus BB, right? Just by using the same definition of the anti-commutator, and this obviously, it's just adding the same thing twice. But this is meant to be 0 in a way that's analogous to this relationship for the annihilation operator for the bosons. And then you can, of course, guess what's coming next. You do the same thing also for the creation operator. And this is meant to be analogous to the commutation relation between creation operators. Like this. So all of them just replaces the usual commutation relation among the creation annihilation operator for the bosons by anti-commutation relation. You switch the relative sign here from minus to plus, and the anti-commutation relation looks the same in the end. So BB dagger is 1 in a way, same way that AA dagger is 1. BB is 0 in the same way that AA is 0. B dagger is also 0 in the same way that A dagger is 0. So that actually turns out to be the answer. But of course, we would like to understand why this is a good thing to do. And the idea is very simple. You again start with the vacuum state. Vacuum state, which by definition is annihilated by the annihilation operator, meaning that there is no particle in it. Then you define the state with one particle by acting creation operator on it. And then you try to create yet more particle by acting creation operator on top of it. And by definition, one particle state was created by the creation operator out of the vacuum state. But now what we see here is looking at this B dagger anti-commutator. B dagger multiplied twice is identically 0. So this vanishes. And that's the meaning of you cannot put more than one particle into the same quantum state. And in general, when you have multiple quantum states, you do this in the same way that you have done with the bosonic harmonic oscillator. So if you have multiple B's for different quantum states, again, you satisfy this anti-commutation relation. In this case, I can write it as twice, because these two are not the same thing. Ji vanishes in the same way that the bosonic creation annihilation operators satisfy these commutation relations. So if you have multiple quantum state, then this is actually one particle state with I state, but I haven't filled the J state yet. This is still the vacuum state. Then I can act BJ dagger on this state, and that will be both I and J occupied. But if you try to occupy J twice, then you would act J creation operator on top of this state where J is already occupied once. And by definition, this state was created by this creation operator. And by the virtue of, again, the same canonical anti-commutation relation, Bj diagonal twice vanishes. That's 0. So this is the way you can treat any quantum state of your interest using these canonical anti-commutation relations. For example, if you're interested in a state of some large atom, like, I don't know, argon, it's not very large, but anyway, the argon atom has how many, 18 electrons. So you need to bring in creationization operators for 18 choices for I and j. And for each I and j, you can use creation operator to put one electron into that state. And in that case, of course, the j has to specify both the orbital and the spin orientation. Then this way, you can occupy each orbital for definite spin orientation only once, but not twice. So that achieves the goal of the Pauli's exclusion principle. So idea, I hope, is very simple. So once you accept this, then you can see that that automatically satisfies the Pauli's exclusion principle. Okay, let me stop here. Any questions? Yes? Sarah? Okay.
I think I remember when we were using AA operators, that has symmetry.
Uh-huh.
Is that the reason why we're using B instead of
That's right. So this actually ends up giving you this anti-symmetric wave function, and we will talk about that in a moment. Okay? Any other questions? Yeah, this is probably sort of simple enough idea. By the way, I hate this name, Pauli's exclusion principle. The physics community is supposed to be inclusive, not exclusive, right? So we are supposed to be open to anybody, but the Pauli's exclusion principle is a way of putting that once I'm here, you're excluded. I hate that idea. So I've been claiming that we have to actually rename this principle to diversity principle, because the idea here is that every electron wants to be different from each other. That's exactly what diversity is about. But unfortunately, even though I've been calling this already over the years, it hasn't sank into the community. So please advertise that name with a very happy time. Okay. Now, coming to this question of anti-symmetry. So obviously, what you're supposed to do from here to the field theory is to extend this idea now to the position space. So that you introduce canonical anti-commutation relation for fields. Now field, of course, is meant to be functional space. Definition is the same. Now plus that's the definition of anti-commutator, which is given by the delta function. So the only change from boson is that this is now anti-commutator instead of commutator. And among the annihilation operators, now we are supposed to anti-commute. And same among the creation operators. And this immediately tells you that the wave function is anti-symmetric. So if you think about, let's say, two-body state, just like in the case of boson, any state of your interest, capital psi, can be written by creating one particle at position x, another particle at position y, and take linear superposition with some arbitrary function, which has the meaning of the wave function in Schrödinger equation in quantum mechanics. But now, if you interchange these two, using this canonically anti-commutation relation, writing in this order, and writing in the opposite order, has minus sign in between, because I moved this second term to the other side of the equation, that gives you the negative sign. So changing the order between two creation operators would give me a minus sign. But in this expression, x and y are dummy variables. You integrate over them. So I'm allowed to relabel x by y and y by x. And because I relabeled y by x, this is now psi diagonal x, x by y, so that's psi diagonal y. And same here, this function is now yx. And integration volume doesn't depend on order, so I switch back to dx dy. And then what you see here is that from here to there, that's exactly the same thing as what you start out with. But the only difference is that now the arguments are switched between two particles at the expense of getting minus sign. And that's the anti-symmetry of the wave function. If we interchange x and y, you get minus sign. So what do you learn in quantum mechanics about the multi-particle system? You have to impose symmetry in the case of bosons, and anti-symmetry in the case of fermions. But once again, just by accepting this canonical anti-commutation relations, anti-symmetry of the wave function just follows. So that's an extra input you have to impose on a wave function. You don't have to anti-symmetrize it. The states come out already anti-symmetrized thanks to these anti-commutation relations. So this is an exact parallel of what I have seen already in the case of boson. But now you can see you can also accommodate the Fermi statistics. Yes?
So is this the same field operator that we're using for bosons? Are we
That's a very good question. So it turns out that it's a different operator. And so that's the actually real subject I come back to talk about. It turns out that when you actually take the classical limit, in the case of the Bose field, you got a regular classical wave. And we spent a fair amount of time talking about this and looked at various experimental data that collection of bunch of bosons really start to behave like a classical wave at a very low temperature and in a dilute gas. Now, what is then the classical limit of this? So classical limit of any operators is that when you have two operators that don't commute, but if you go to classical limit setting h bar to 0, they of course do commute because they become just numbers. There's no concept of operators in classical mechanics, so everything is supposed to commute. But what you're seeing here is something rather bizarre. If you think of classical limit of some kind, something that gives you delta function in classical limit should go to 0 in the same way that commutation and anti-commutation relations, they should commute in the classical limit. So now you're talking about some weird object where they have to anti-commute in classical field. Classically, everything anti-commutes. So if we have two observables A and B, quantum mechanically they are operators. So even if you set up something about anti-commutator, it might not sound strange, but in classical theory, they're supposed to anti-commute. So two objects A and B would change their signs when you reorder them. Now this looks really weird. But this kind of thing is at least possible mathematically. And they're called Grassmann numbers instead of ordinary numbers. And sometimes it's just emphasized that they have to commute by putting the word odd in between, because that's odd. So you can say this is the Grassmann odd numbers instead of Grassmann even numbers that are the ordinary numbers. And this looks very exotic. But if you think about this, first of all, mathematicians tell us that there's nothing really inconsistent about this kind of algebra. So it's okay. So surprising thing that nature decided to use it instead of something we're facing inconsistent. So it's actually totally okay. And if you further think about it, you have seen some things that may anti-commute. For example, if you have an inner product of two vectors, and this is AX, AY, AZ, this is BX, BY, BZ. But these are just vectors, they're not creation or relation operators, so let me change my notation to avoid that possible confusion here. And this is AX, BX, AY, BY, AZ, BZ, as everybody knows. And this, of course, is the same thing as B dot A. So inner product doesn't depend on order between them. So this is sort of like a boson. But exterior product is a vector, and x component of exterior product is AY, BZ minus AZ, right? And y component is z and x, and z component is x and y component. And because of this minus sign in this definition of the exterior product, if you change the order between A and B, this becomes BY AZ. The BY AZ. That's the same thing as BY AZ over here, but at the expense of minus sign. And same thing over here. So this is actually odd under the interchange of two vectors. So this is something you have already seen in vector calculus. You have some kind of multiplication going on here, but this multiplication depends on order of two objects. And when you switch them around, you get a minus sign. So this looks very exotic, but you actually haven't seen this before. So there are definitions in mathematics where you define some kind of multiplication of two objects, but they anti-commute instead of commute, which is perfectly okay, and we have seen this before. Okay, any questions about this argument?
So would you say that, I guess, pseudovectors are Grassmann? Would that be?
You can say that. Indeed, so that's right. So there's a generalization of this exterior product in mathematics called differential forms, and they always anti-commute. So people write something called a wedge product. And integration volume is actually this wedge product. And this actually anti-commutes when you change the order, in this case between x and y. And this is Grassmann arc. And this is what is called the differential forms. So this definition of exterior product is strictly within 3 dimensions, but there is a generalization you can think about in arbitrary dimensions. So you can have arbitrary number of things that have to commute among each other, and the differential forms in math that appears in differential geometry is again one example of it. So what you are seeing here is that at least mathematically, there are many algebras where you introduce some kind of multiplication between two objects, but when you multiply two objects together, A and B, and if you switch them around, you always get a minus sign. And there's nothing wrong with it. So this is the idea of Grassmann arc. And if you just reflect a little bit more about this, you have been expanding the idea of what a number is. Already, you start with integers, maybe natural numbers. One, two, three. That's something you may learn when you were in kindergarten. But when you actually get to, I don't know, maybe middle school, you start to learn about negative numbers. So in addition, these positive integers, you have these negative numbers. You have expanded your notion of what a number may be. Then you have also rational numbers that you may have 2/3, 5/7, minus 1/5, and so on. So now these are non-integer numbers, and I don't know when you learned this. That's in elementary school, I guess? Is it? Fourth grade? Okay. And then you further expand this to real numbers, like pi or e. They are irrational. And that's already a surprising thing. You can write them in digits, 3.14159 dot dot dot. It just keeps going. There's no regularity among the numbers. And you can never write this in terms of these fractions. And apparently, Pythagoras, of course, is a famous mathematician in ancient Greek, but he was kind of cult leader, apparently. So he had a group of mathematicians, his pupils, and they had this belief that everything in the universe is basically numbers. Number is everything. And he apparently also believed that every number has to be rational. But irony is that using his theorem, if you have a triangle with two sides of 1, then this side is square root 2, that's irrational. And one pupil over here proved that this number cannot be a rational number. And apparently Pythagoras was so mad at this pupil, so he killed him. Now, I don't know if it's true, but that's the story I read in books. So he got this sort of cult leader-like character that he really believed in these things. And everything was supposed to be sort of beautiful numbers. And one of the things I also like is I like music a lot. And when you have a string with the same tension, and if you have the ratio of 4, 5, and 6, that's the major chord, like C. You can write, for example, C, E, and G. So the beautiful harmony comes with integer ratios. And that's really true. If you play any string instrument or guitar, you are actually probably familiar with this fact. So beautiful sound has to do with the beautiful numbers. So that's the kind of sort of belief he had about how the universe works, and hence he couldn't believe that there can be irrational numbers. But anyway, so we now know there are. So we again expanded our notion of numbers. And the last thing you have done is to introduce complex numbers by introducing square root of -1. And we say this is imaginary. And of course, you have gotten used to the idea of imaginary numbers, but if you look at this name here, imaginary, that clearly indicates that when people came up with this I first, they didn't think this was real in sort of the usual sense. They don't exist. They are imaginary. That's why they call that imaginary numbers, I suppose. And then after introducing these imaginary numbers, you can start building numbers like this. That's a complex number, has a real part, an imaginary part. Either one of them could be rational or irrational. And then we're talking about these complex numbers. So you have come a long way. You kept expanding your notion of numbers. And probably the first time where imaginary number becomes real, the real in the sense of something tangible and you can touch it and work with, is the quantum mechanics. Before the invention of quantum mechanics, imaginary number was not really necessary for any physics. Maxwell's equation is written in terms of all real numbers. Electric field is real, magnetic field is real, Lorentz force is real, everything is real. But when you get the quantum mechanics, you have to accept all of a sudden that your wave function satisfies the Schrödinger equation with I prominently at the very beginning of the equation, and you accepted that. So it's actually not strange that you have to expand your notion of what numbers do when you face new physical phenomena. And the idea of Perversity Principle was a new thing to Pauli. People didn't know that before, so that was the invention in the early 20th century. It didn't exist in 19th century. So when you have to face something like this new, sometimes you have to accept there is a new kind of number that anti-commutes instead of ordinary numbers you've been used to, which commute among each other. So it's, in that sense, I don't think that's really new. But you just have to get used to it. Any questions about this argument? Yes. Okay.
I have a very simple question. So, is the motivation of creating the anti-commutators just for fermions?
Yes.
Or, okay. Okay. Got it.
And then what you know is that when you actually see a Lagrangian, which is always a starting point of QFT or quantum mechanics, and when you actually look at this Lagrangians, first thing you have to know is whether, already at the classical level, is this Grassmann even or odd? So when you write this Lagrangian, this is written as a function of this field, psi, but before even quantizing it, you have a choice whether this is the commuting numbers or anti-commuting numbers. You have to choose which one you are using in your Lagrangian. And once you have made a choice, then you go through the usual quantization of setting up the canonical commutation relation. But because in the classical limit of sending h bar to 0, whether your operators could commute or anti-commute, then you are now required to use commutation relation when you have made a choice of using Grassmann even number for the field or anti-commutation relation, which reduces the Grassmann odd numbers in the classical theory. So once you have made a choice when you write the Lagrangian, whether you have to use the Grassmann even number or whether you have to use the Grassmann odd numbers, the rest follows, and you end up with commutation relation, and then you are talking about theory of bosons, or you end up with the anti-commutation relation, then you end up with theory of fermions. So once you actually know what number you use to write down your Lagrangian, then everything is now automatic. That's not any additional input beyond writing a Lagrangian. Does that answer your question?
Yeah.
Okay, good. Any other questions? Yes? That's
Are
all.
the Grassmann odd numbers a group with the product?
Yeah,
And
so,
like if I do like the second question would be like any power of like a Grassmann odd number apart from like 1 is 0.
yeah, any product Grassmann odd numbers, the same one twice
Yeah, okay.
is actually half of the anti-commutator, and therefore it vanishes.
Okay. And it's a group.
Oh, well, no, I misspoke. It's not a group because there's no inverse element.
Oh, okay. Okay.
You know, there are actually people who talk about that too. So I'm not too familiar with this, but there is an idea in group theory where you extend also the commutation relations, including anti-commutation relations, and you have some kind of group-like structure with that.
Okay.
So maybe I shouldn't say it's not. It depends on what kind of
What you
algebra
need.
you're dealing with.
Okay, thank you.
So this is an algebra,
I'm sorry?
is this an algebra?
It is an algebra, yeah.
Take 113.
So algebra,
Oh, just math 113 is abstract algebra. It's a very fun class.
I'm sorry?
Math 113 covers a lot of this abstract
Oh, is that right?
algebra. Yeah, it's a very fun class.
Okay, great. So that's class of algebra.
Yeah.
Yeah. So the algebra means that you have some linear space where you introduce the usual additions and multiplications of numbers, but you also introduce this kind of product among any of the elements, and then that's an algebra. And this Grassmann odd numbers is an example of algebra. That's why mathematically there's nothing wrong with it. So it's an algebra when you define the product with what mathematicians call ideal. In our case, this being 0 is ideal. And you mark out your linear space by the ideal. That's the definition of an algebra. And so it follows all those standard rules of how you define an algebra in mathematics. Am I saying this right? Okay, good. Yes.
So whether they're odd or even, the commutation relation remains the same.
This one?
The commutation relation.
In the case of usual numbers, you just define again what mathematicians call ideal. This
No,
way.
I mean over there, whether you choose to be even or odd.
Here?
Yeah, over there it's always a delta function.
Yeah, that comes from the fact that you define the canonical momentum to psi using the derivative respect to the type derivative one. So this one is the canonical momentum with respect to the canonical coordinate.
So then how is there any change if we choose it to be Grassmann even or Grassmann odd? Because in both cases the commutation relation remains the same, right?
So that's because when you think of the classical limit, when these things become 0, then you find that this is the Grassmann odd anti-commuting numbers.
Oh, I see.
Yes?
Just if people are interested, I believe this would be a ring because we have a multiplication operation that does not have an inverse and addition.
That's right. That's why it may not be a group.
Yeah.
But it's still an algebra.
Well, it's a group under addition, and then
Well, if we're defining that it has the identity,
Yeah.
if it has the identity, it would be a group within the ring, but if it doesn't have.
You need to have identity element and the inverse element.
well, we have the identity for addition.
Not necessarily multiplication.
Yeah, so it's a group under addition.
Yeah.
So then it's a ring when you have multiplication.
That's right. That's right.
Yeah.
But not under multiplication
Yeah.
necessarily.
Yeah.
It is not a group under multiplication.
Hey, thank you. Any other questions? Yes, Sarah.
Still wondering, what do you mean by everything anti-commutes?
Okay, so let me also make it clear. Thank you for the question. So in general, you have QFT with both fermions and bosons, right? If you're talking about electromagnetism, you have an electron, that's fermion. And you have photon, that's boson. So what we end up doing, so we get to quantization of photon after we are done with the fermion, you introduce a field for electron that does anti-commute. And for photon, we have to use an electromagnetic field. And they satisfy commutation relation because they are bosons. And this actually turns out to be a little bit tricky to write down. This is actually derivative of wait a second. We'll come back and talk about this later, but at least you can see that the boson is supposed to be described by commutation relations, and photon ends up being described by the electromagnetic field E and B, and so E and B are no longer numbers when you quantize it, but they still satisfy commutation relations instead of anti-commutation relations. So we have a QFT where you have both kinds of numbers, both Grassmann even and Grassmann odd. Then to answer your question, the rule is that when you have odd, you have to use anti-commutation. But whenever you have even objects, you use commutation. For example, when you ask the question, what happens between the product of electric field and the electron field, then they commute. Only time you are supposed to use anti-commutation relation is that you multiply two Grassmann odd objects. In addition, when you have the product of two Grassmann odd objects, for example, this is the number density of electron, right? We've been talking about this number density all the time in bosons and condensate. This product of two Grassmann odd objects is actually Grassmann even. So think of this being really just, the negative numbers or something like this. If you have two negative numbers, you multiply them, you get something positive. So the Grassmann odd objects multiplied even times becomes Grassmann even objects. And that's something you can prove. Oops, sorry. I wasn't planning on doing this, but anyway. So let's say alpha beta are Grassmann odd, A, B, Grassmann even. Then you ask the question whether alpha beta, the product of two Grassmann odd numbers, multiplied with the Grassmann even number, whether they anti-commute or commute. And so in this case, I compare this object and that object. And here I use commutation relation between beta and A, because odd even are supposed to commute. Then I use the same rule here between alpha and A. Again, odd even are supposed to commute. So as a result, alpha beta as a product commute with Grassmann even object. More interesting question is what happens when you have Grassmann odd object over here. Then beta and gamma, both being Grassmann odd, should anti-commute. So I get a minus sign when I interchange the order between beta and gamma. But now you focus on alpha and gamma. Again, both of them are Grassmann odd. So when you change the order, you're supposed to get a minus sign. So this becomes plus. And what you see as the end result is that this product of two Grassmann odd numbers, alpha beta, end up commuting with the Grassmann odd number gamma. Therefore, alpha beta has to be even. So that actually is a good idea, because when you think of observable like a number density, you don't want the number density to be this weird Grassmann odd number. There's something you can measure, and that has to come out as a regular number. You say the number density of atoms is, in the BEC problem, you had this, the density of air divided by 100,000 something. It's a number. So when you measure the density of electron, that is also supposed to be a usual number. And indeed, this is a product of two Grassmann odd numbers, and hence this is a Grassmann even. So that comes out to be the ordinary number at the end of the day. So that makes sense. The only thing is that you have to be sort of super careful when you get used to it, because whenever you interchange order between two things, you are just used to the idea that you can just freely do that, but now you can't. You have to carefully follow in which order things are multiplied on top of each other. You have to pay attention to which one is Grassmann odd, which one is Grassmann even. And when you change two Grassmann odd numbers, you have to put carefully the minus sign whenever you do so. So you have to be a little bit more careful than what you're used to. But again, nothing is mathematically inconsistent. You just need to do this algebra a little bit more carefully. Okay, does that answer? Whose question was this? I forgot. Oh, sorry. Okay, does that answer your question?
I'm still not sure how we can say everything classically. Like what goes under, what do you mean by everything?
Oh, everything is what I get. When you have some quantum theory, you have all kinds of operators in it. But when you go back to classical mechanics, then those observables all end up being either Grassmann odd or Grassmann even numbers. So they either anti-commute or commute. So that's what I meant everything. So any operator you have in quantum mechanics, when you go back to classical theory, you set h bar to 0, then all of those operators become numbers. But some of them end up being Grassmann odd numbers. Some of them end up being Grassmann even numbers. And they follow this rule in the classical limit. That's what I meant as everything. Does that answer your question?
Yeah, more or less. Okay.
More or less.
Yeah.
Okay, so if something is still not clear, then just ask more questions later on. Yes?
So before, when they asked if the field operators are the same or different for the fermions and the bosons.
They're different.
They're different, but they're not different in the fact that they create a particle, right? They're just different in the fact that they do commute or anti-commute.
That's right, that's exactly right.
Okay.
But that difference ends up being either fermion or bosons, because when you have the Grassmann odd numbers, you can't multiply two creation operators to get something non-zero. That automatically vanishes thanks to anti-commutation relation. And that's how you implement the exclusion principle or delusion principle. Okay, any other questions? Yes?
Can I assign values to Grassmann odd numbers? Like, can we see that the Grassmann odd number is equals to 1 or 2?
No, because 1 and 2, by definition, is a number that commute among each other. So then, if you write Grassmann on field being 1, then both sides of this equality end up being inconsistent with each other. So they cannot have numerical values. Yes? Okay.
Yeah, okay. So I have a question. So now we have three concepts. First is field, second is operators, and the third is Grassmann numbers. But in the quantum field theory perspective, we connect the idea of field and operators. Then, under which conditions should I consider it as a number? Because
So it's a Grassmann odd number. It's not number like 1 and 2. It's not number like complex numbers, but it is still a number.
It's just describing how they interact
Right,
with
right.
each other. It's not saying this is like
okay,
some
not
natural
absolute
integer or
values.
something.
Okay, got it. Okay.
So again, you're expanding the notion of number, and you're looking at a wider category of things, but it's still a number, meant to be a number. Yes.
Can two numbers, like two matrices, be both Grassmann odd and Grassmann even? So for example, the zero matrix and the identity matrix.
Identity matrix is by definition something that identity times anything else is the same as something else. So that by definition that commutes, right?
Yeah.
So 1 times A and A times 1 are both A. So identity element has to be Grassmann even number.
Wait, so the Grassmann odd numbers are not actually numbers, they're just like some like mathematical objects that follow the anti-commutation relation.
So that depends on order by number. So this is, you can call this is a number 2, but your notion of number has to expand. So it's not the number you are used to, but it's a number, mathematically.
Okay.
Is that okay? Yeah. Any other questions here?
So we're just essentially calling operators numbers by
In the
defining,
classical limit, yes.
by defining an
Right,
algebra.
right, that's right. Yes.
This is the same algebra as like vectors where multiplication is cross product and where we're adding, right?
Yeah, it's the same idea.
Same, yeah.
Uh-huh. I saw another hand, yes.
If we go back to classical limit,
Uh-huh.
is there any physical variables that corresponds to odd Grassmann?
They are not numerical numbers, so that's why there's a clash of your concepts. So normally, when you have a field like this one, it's a field as a function of x, but you are talking about this position field is 2, at this position field is -1. They are still numbers at any position in space. But Grassmann odd field is that every position in space is a Grassmann odd number. And that number is not 1, 2, or square root 2. It's a different concept. But we still regard them to be numbers. So now I actually would like to use it. So I define how you can deal with the fermion in QST. And now we'd like to use it. And we always, of course, start with 3 particles because they are simpler. And of course, in the end, we'd like to put interactivity there too. In the case of the boson, in a homework problem you're doing right now, you're looking at this Hamiltonian in part A, and I ask you to show that this doesn't have a ground state. Right? That's the first problem. When mu is positive. Only when you introduce the repulsive interaction among the bosons, you find the ground state, which turns out to be Bose-Einstein condensate. Now I ask the question, what happens if this is a fermion? In this case, it turns out that there is ground state for fermions, even when mu is positive. So there's an essential difference between boson and fermions already when you look at the free particles. And the idea is that when you have this Hamiltonian, and when P is big enough compared to the chemical potential, this thing in parentheses is positive. So the ground state is annihilated by annihilation operator. But when P squared over 2m is less than mu, you can lower the energy by occupying the state. In the case of boson, you can keep putting more particles into the state, that's why there is no ground state. You can keep lowering the energy indefinitely. But in the case of fermion, you can't do that. To lower the energy, looking for the ground state, you first occupy the state. But you can't put any more particles into the same momentum mode, so it stops. So for momentum mode, which satisfies this inequality, This is the ground state. So what I'm saying is pretty simple. You guys do a friction. So this is where P is what? 2mu square root. And the idea is that for all momentum modes below this momentum, you put one particle in there. For all the momentum modes above this value, you don't put particle in there. So your ground statement is product of creation operator for all momentum whose kinetic energy is less than mu on the vacuum state. But you don't use creation operator for momentum modes above this number, so they are vacant. So here occupied, here is vacant. You fill particle here, you don't over there. Yes?
Wait, are the possible momentum states for a free fermion no longer continuous?
Momentum space is continuous. I'm assuming P is continuous.
Okay.
But here you have a step function. Below this momentum, you occupy that state. Above this momentum, you don't occupy that state. And another way of seeing the same thing is that if you draw this parabolic form of energy, here is the square root 2mu, and up to this value, you fill all these states. Maybe I should draw bigger. But above this, all the states are empty. And it turns out that's exactly what an object like this one is doing. Metal. Inside a metal, you hear about this idea of nearly free electrons. That's why when you apply the electric field, all the electrons start to move, and that's how you get electrical current. So electrons can move inside the metal. But it turns out that all the electrons occupy momentum space only up to a number because they come with a finite density. The reason why they can conduct electricity is that when you apply an electric field, then energy changes to something like this. So what used to be occupied can become vacant, or what used to be vacant can become occupied after this shift. So these extra states that are occupied now correspond to electrons that are moving inside the system, and that's the electrical current. So your iPad and iPhone don't work if you don't have this kind of system. So metal is what people call Fermi, namely that you occupy all the states in an ocean up to some depth. And the depth is defined by this upper limit on momentum you occupy. This is what is called the Fermi momentum. Or some maximum energy you occupy, which is called the Fermi energy. So the idea is that when you pick up a piece of metal, electrons in that piece of metal is actually a Fermi seed. It's described by this state. Now it's very easy to characterize. Ground state is annihilated by all the relation operators when P is equivalent to M is bigger than mu. But for momentum mode, which is below the Fermi momentum, it satisfies rather this condition, because that state is already occupied. The condition is that you can't put more electrons in there. And this is again the advantage of QFT. If you have a piece of metal then there are Avogadro number of electrons in it. You don't want to write down the multi-electron wave function x1, x2, x 6.02 times 10 to the minus 10 to the 23. You don't want to do that. But in QFT, all you have to do is say that your ground state is what satisfies this condition. You don't need to write this Avogadro number of times. So that's the idea. So even already for the case of the free fermion, it's already very different from bosons. With a positive chemical potential, you still have a well-defined ground state. But just like BEC, the ground state is not the vacuum state because of chemical potential. Chemical potential gives an incentive to put particles into the system, and as a result, the ground state does have particles in it, but only up to the energy given by this Fermi energy. So you have a system with a bunch of states, and up to Fermi energy, you occupy all of them with electrons, but you keep all the states above the Fermi energy vacant. So to avoid the confusion, let me remove this again. So all the states below Fermi energy are occupied. That's the ocean, that's the Fermi sea. And above the Fermi energy, you do not occupy the state. They remain vacant. So this actually turns out to be the ground state of that Hamiltonian. So this is again free particle, so no interactions among them. But you already see that talking about fermion is already something interesting. Positive chemical potential still gives you well-defined ground state. And that ground state has a bunch of electrons in the system, occupying up to Fermi energy. And then in the case of a piece of metal, the Fermi energy turns out to be something like several thousand degrees. So at the room temperature, then it's really at the ground state. You can ignore the excitation that is Boltzmann suppressed. So inside this, it's really this kind of state. And so
this may not make a whole lot of sense, but why can't we because we've drawn the electrons as if they're at higher and higher momentums, why can't we just find another lower energy state by just smushing them closer together in momentum space?
So when you introduce interactions, you kind of have a situation that looks something like this.
Okay, so it's the interaction between them that makes this the ground state.
But we're talking about the free particle right now. So
Yeah.
in the absence of interaction, then this is really the exact eigenstate of that Hamiltonian.
Okay.
And we will talk about introducing interaction later on. And when they get severe like this one, and that is actually so the analog of BEC fermions called superconductor.
Okay.
So in the case of boson, we have this idea of superfluid. Things actually flow without any viscosity and resistivity. In the case of electrons, you have something similar to that. Then that idea is called superconductor. Namely, fermions can again flow without any resistivity, and hence you have actually a very nice material for the purpose of, for example, in the future, we hope to design a grid, electrical grid, with superconductor. Then there is no loss in transmission. And that's still a dream. The technology is still being developed, but that will really be a green technology in the end. So people are working on that. Any other questions at this stage? Is it great? Okay. So just by changing the Grassmann even number to Grassmann odd numbers and writing down the Lagrangian like what we used to, without interaction, but with positive chemical potential. And when you rewrite this in the momentum space, that will be the next homework problem. Then you can really show that Hamiltonian is indeed this. And now we have found the ground state, which is an finalization operator for states above the Fermi energy, and Fermi energy is indeed given by the chemical potential. I forgot to say that, right? Because you occupy up to the state given by the chemical potential. So the Fermi energy is nothing but the chemical potential. And instead, you cannot put more particles into the system if you're below the Fermi energy. So that actually turns out to be the ground state. And I mentioned metal here, but there's another famous object in our universe which is made of Fermi seed. They're called white dwarfs. So as you know, star shines because it's creating energy in their cores by the nuclear fusion process. Protons and neutrons inside the core of the star would fuse and form bigger nuclei. And because of the binding energy of the nuclei, that process would release energy. And because that releases the energy, that will make the surrounding gas hot. Hot gas means anything inside microscopic particles, nuclei, electrons are moving fast. And when objects are moving fast, they will bump into each other with gusto, meaning they hit each other with force. That creates a pressure. An idea of a star is that this pressure balances against the gradient of density which comes with gravitational force, so that this is actually a hydrostatic equilibrium. Which is just a fancy way of saying that pressure wants to push the gas outward, gravity wants to pull, and if they balance against each other, they will reach equilibrium, becomes a static, stable object, and that's how stars work, as far as we can tell. And we even have an evidence that the nuclear fusion process is happening inside the star, because in our star, over there, which direction is it now? I don't know. Sun is that way? So it should be somewhere that direction now. So our sun is about to doing this too, but when it actually does this, two protons come together, and at the end of the day, you bring in four protons together, and that becomes helium. Which has a binding energy of about 25 mega electron volts. That's a lot of energy, and that's why it can release energy. But now you see that proton has changed to neutron. That doesn't conserve electrical charge, so you have to somehow spit out positive charges. So this process created two positrons. That's an antimatter. And when we quantize relativistic field, we actually see that antimatter is a protection of QFT, and we'll come back and talk about that. But that way you can conserve charge. But then you are not conserving something different called lepton number. So you have to also produce two neutrinos from this process, it turns out. The neutrino is a particle which interacts so little. And as we speak, there are something like what's the number? 10 billion, 100 trillion neutrinos going through your body every second. And they come from the sun. And even though you're inside building, neutrinos interact so little that they can just punch through all of this concrete without any problems. Even when you're in a bed in the night, when the sun is on the other side of a planet, they just go through the entire Earth without any problems. So you still get 100 trillion neutrinos a second through your body. So it's a very shy particles. And when you have this process, it of course produces energy, produces light, but sun is so dense that light cannot escape because it keeps bumping electrons. Thomson scattering, or Compton scattering if you like. So you can't get the photon just come out of the sun very easily. It takes about many thousands of years for the photon produced from nuclear fusion process to get out of the sun and eventually reach us. On the other hand, these neutrinos are so shy, once they are born from this process, they can just go straight out from the core of the sun and then reach the Earth. And people have seen those. So there is an experiment in Japan called Superconductor, which is a huge water tank, like 40 meters high, 40 meters wide. But when the neutrinos come in here, most of the time, just keeps going. But once in a while, because it's such a big target, it can knock an electron out of the water molecule. The electron has the energy of multi-mega electron volt, so it's actually very close to the speed of light. But inside the water, the speed of light is smaller by the index of refraction of like 1.25 or something. So it turns out that the speed of electron inside water is faster than the speed of light. Nothing wrong with relativity here because speed of light has slowed down. It's not faster than speed of light in the vacuum, but it is faster than speed of light inside the water tank. And so that actually gives you a shock wave. That is called Cherenkov light. Just like the supersonic jet would produce a shock wave, the same idea. And you can detect this light and tell that it's actually an electron. So they, experimentalists, have looked for the sun in pitch darkness 1 kilometer underground. No light comes in, but neutrinos do come in. But they see this only occasionally because they interact so little. So, if you're looking at some very dim object where you don't get that much light, you have to keep the exposure open. And if you're taking a picture of some star or galaxy, you have to keep following it over a long period of time. And then you can take a picture of that galaxy, for example. You have to do the same thing. You keep the exposure open for 5 years in this case, because you only get like 10 neutrinos a day. But if you do that, they could actually see the sun. And I will give you the picture and post that on our slides later on. So they actually could observe the neutrinos coming from the sun underground in pitch darkness. And they took the picture of the sun. It's not a photograph, but neutrinograph. And that's how we know that nuclear fusion process is indeed happening in our sun. So that's an experimental evidence for that. But now comes the problem. Sun would eventually use all of its nuclear fuel. The nuclear fusion process would eventually stop. Then you don't create this pressure anymore because it doesn't create energy. So what would happen to it? Clearly, there is no pressure that resists the gravity, so everything starts to shrink. But it comes to the point that once it becomes small enough, then all the electrons inside this original gas of the sun become this Fermi sea. And once that happens, then the electrons form a very, very dense gas now, occupying up to some Fermi level. But if you like to squeeze it even further, you can't do this because that would require putting 2 electrons occupying the same position or same momentum. So being Fermi, the general Fermi sea, is actually a way of resisting gravitational pull. So there is a pressure due to this Fermi sea. If that's the way you can support the entire star, then you're calling this a white dwarf. So what happens in this case is that we have the sun, we are orbiting around it, and there's a nuclear fusion process that gives this pressure. But once that's over, you can't resist gravity, so everything starts to shrink. And everything on the outside, that's the rebound. And the sun becomes as big as our orbit. So we get either swallowed by the sun, or maybe being sort of kicked by the coming surface of the sun. So either way, this becomes a scorching hit the planet, so we can't live there anymore. So the climate change is probably becomes much faster than this, but eventually this will become hell. We can't live there anymore. So because you're young, you have to come up with a plan B somehow, and so you have to design a spaceship and make sure that you can leave the planet. And this happens in about 5 billion years from now. But anyway, so then what's left in the middle is this white dwarf. So the idea then is that once we have this Fermi sea that resists the gravity, you can do a very simple back of the envelope estimate how that works. So you occupy all the states up to Fermi momentum, and that gives you some kinetic energy of the system. And total kinetic energy of the system then would be adding all the momentum modes up to Fermi momentum and kinetic energy for each particle. And once this happens, it turns out that the electrons eventually become relativistic. So kinetic energy is speed of light times momentum. And sum of all the momentum modes in 3 dimensions, px, py, pz, can be just done by the volume in momentum space and the size of the star, and this also is multiplied by another factor p. We're doing just estimate, so let's not worry about do a proper integral like this. So at the end of the day, total kinetic energy will be volume for momentum to the 4th power times speed of light over 2 pi h naught cube. Then this has to balance energy of the gravity with the Newton's constant, the gravitational energy on itself. So the two masses are the mass of the star over its sides. So roughly speaking, this is the gravitational energy. And everything is supported by the pressure coming from this Fermi degenerate sea. They are supposed to be more or less equal to each other. That's the back of an estimate. Then you can just work it out. And I don't do this, but you can look at the slides later. Then you find the mass of such a white dwarf should be given in the end like this. Mass of the proton neutron comes into place because the mass is basically number of electrons times the mass of the proton. That's the mass of the star, so that's how you have dependence on the mass of the proton. And if you plug in these numbers made of fundamental constants, this is 3.7 times 10 to the 30th kilogram. And for comparison, mass of the sun is this. So the surprising thing here is by putting in these fundamental constants of nature, you can work out the mass of a star. That turns out to be about the mass of the sun. And it turns out that there is actually a famous limit by Chandrasekhar, an Indian physicist, who have shown rigorously that the mass of the white dwarf cannot be bigger than 1.46 times the mass of the sun. So white dwarf cannot be heavier than this. And that actually turns out to give you a very useful tool in astronomy, and I ran out of time, so let me stop here. But what I want to tell you is that this Fermi sea has a pressure, which is called the Fermi degeneracy pressure. And this Fermi degeneracy pressure can support an entire star. And that turns out to give you the upper limit on the mass of such an object, worked out by fundamental constants, which is about the same as the mass of the sun. So the microscopic physics really tells you the mass of this macroscopic object. And I find that really fascinating. Okay, let me stop here. I'm sorry I ran out of over time.
If it's like more than that, you would get a black hole.
I'm sorry?
If it's more than that, you would get like a black hole.
No, if it's more than that, it's okay.
If it's